So, hello everyone, today I will start the module 4 protein surface interactions. So, the first lecture will be the protein adsorption. So, I will recap the module 3. So, in module 3 we discuss the measurement of surface tension. In the first lecture we discussed the surface tension of liquid. So, in that we discussed different methods like a detachment based method like ring method, plate method. Then we discussed analysis of drop shape. Then also we discussed few dynamic methods like the flow methods. Then followed by that in the next lecture we discussed different method to measure the contact angle. So, there we discussed the sessile drop method, plate method, and for the powder samples we discussed the porous plug method. Also we discussed the difference between the static and dynamic contact angle and related with the contact angle hysteresis. In the last lecture we discussed how to calculate or determine the surface tension of solids. Because of the rigidity and elasticity and plasticity of the solids, they do not behave like the liquid. So, we cannot apply the same method which we use to determine the surface tension of liquid. So, for the solid we discuss few methods depending on its melting, its solidification, its solubility. Also we discuss the indirect method where we can determine the surface energy of solids by measuring the contact angle of two or more liquids. Also we discuss the work of adhesion. We can calculate from the contact angle data, we can calculate the interfacial tension, and then we can calculate the surface energy of solids. Also we discuss few methods to determine the adhesion force, and from adhesion force we can calculate the work of adhesion. So, in today's lecture we are discussing the protein surface interaction. So, first I will talk about basic of protein, then different structures of proteins, followed by what is the different classification of proteins, function of proteins. Then we will discuss about the protein folding, and after that protein folding you will see what are different factors which affect the protein folding, or you can say which affect the native conformation of the proteins. So, proteins, as you know, these are the building blocks of life, and this plays important role in all cellular activities, and it is essential for the all living system. So, you take any cellular system, it is always catalyzed by the enzymes or proteins. You take the any transport system, it is all mediated by the proteins. You take any signaling system, it is all regulated by the proteins. So, in the body all the cellular cycles are regulated by the proteins, and they are largest organic component of a cell. Typically a cell contains 18% of the protein and about 70% of the water. In the extracellular matrix it contains again majorly proteins. In the plasma it contains 7-8% of the proteins and water 90%. So, we can say this is the largest organic component of a cellular system, or you can say of the body fluid. Now, protein, you can consider protein as a biopolymer. It is like a biopolymer. If it is biopolymer, so what is the monomer? Its monomer is called amino acids. So, n number of amino acids are combined to make a protein. So, proteins you can say they are the heteropolymer of 20 different amino acids. Now, if there is a 2 different amino acids are coming, so there should be some interaction between these 2 amino acid, and that binding or linkage between 2 amino acid is known as the peptide bond. So, amino acids are linearly linked by a peptide bond. peptide bond is NHCO. Now, once there is a peptide chain, the amino acid chain is there, then they interact with themselves to form a 3-dimensional structure of a protein. Means there is a linear chain having the peptide bonds, then there will be some sort of conformational changes to reach finally a 3-dimensional protein structure. So, we will see what are different structures of the proteins. So, we will quickly see there are 20 different amino acids. So, you can say amino acid as a basic unit of the protein or monomer of a protein. So, this is the structure of a protein. This C carbon, it is having one side NH2, this C carbon, it is having one side NH2, other side it has COOH carboxylic group, here it is having H group and here this will have a R group. So, R group, this defines the what is the nature of that particular amino acid. So, here you are having 2 amino acid, one is having R1 group, other is having R2 group. So, if there are 2 amino acid combines, this is the condensation reaction. This is a condensation reaction where this. So, this will be like NH2 Cr CH C double bond O, this is gone. Now, NH C again R2 H C double bond OH. So, here this CONH, this is the peptide bond. Now, if you just see the amino acid, it is having one is the, you can say amine is a positive charge group, carboxylic acid is a negatively charged group. Again one more functional group will be added R, it may be polar, it may be non-polar, it may be acidic, it may be basic. So, this gives a mesomeric structure to the amino acids which may have the dipole moment, but they do not rotate around the peptide bond, but they may have different orientations or organizations. So, from this 20 amino acids there will be dipeptide, tripeptide, pentapeptide and so on, and depending on that. So, a particular protein may have 20 amino acid, it may have 100 amino acid, it may have few hundreds of amino acids. So, total we have 20. So, we have charged amino acids, there are 2 acidic charged amino acid depending on the R group, 3 basic positively charged amino acids, there are non-charged polar amino acid 7. So, these amino acid also falls in the category of hydrophilic amino acid. Hydrophilic amino acid, while there are non-charged non-polar amino acid, there are 8. The non-polar means it is a hydrophobic. So, now if you just see amino acids are classified as polar, non-polar, positive charge and negatively charged. So, once different combination of these amino acids are present in a protein, so that is why the protein occupies hydrophobic groups, hydrophilic group, positive charge group and negative charge group. So, interaction with even within the protein or protein interactions or protein surface interaction become the complex because of the involvement of different types of amino acids, polar, non-polar, positive charge, negative charge. So, once we are having the primary structure, means the peptide bond between the amino acids, then fold into the secondary structure. So, this is like a spatial arrangement of the primary structure of a linear chain. So, this is a secondary structure, it may have the alpha helix, it may have the beta sheet, the random coil or the beta turns. These are the 4 major secondary structure, the alpha helix, beta sheet, it is the alpha helix, it is the beta sheet, beta turn or random coil. These are the 4 major part of the secondary structure, and after the secondary structure they are again folded into some sort of 3 dimensional structure, you can say. So, this is like a rearrangement again here. So, this is a tertiary structure, and after tertiary structure few polypeptide chains assembled together, and this assembly is known as the quaternary structure of a protein. So, we start with the linear chain primary structure, then we go to the secondary structure, then tertiary structure, and finally the quaternary structure. Now, the function of a protein is totally dependent on its folded structure. So, if it is a properly folded conformation, then protein functions properly. Any disturbance in its folding or the particular conformation, its functions are totally lost. And now, as we see what are different types of amino acids. So, there will be different kind of bonds like hydrogen bonds, disulfide bonds, electrostatic interactions as well as the hydrophobic interactions among a protein because of the presence of different functional groups in a protein. So, secondary structure may have the alpha helix, beta sheet. So, typically we see the alpha helix like a left handed alpha helix. Left handed means we start like this. So, if we take like this is a left handed alpha helix and this is a right handed alpha helix. So, typically we go for a left handed alpha helix. So, if you see the left handed alpha helix here, it is a counter, this is going like a clockwise, this is right handed, this is going like a anti-clockwise. So, if it is going anti-clockwise, it is a left handed alpha helix. So, here between one turn we see there is 3.6 residues, 3.6 amino acids are there between one cycle, and the pitch of this is, this length is 0.54 nanometer. So, the alpha helix may be the left handed means anti-clockwise, right handed means clockwise. So, mostly we have the left handed alpha helical structure where the length between the one cycle is 5.4 nanometer and it contains 3.6 residues of amino acids. Similarly, we will have the beta sheet, then beta turn and the random coil. Now, based on the 3D structure of a protein, we can classify them into 3 categories. The first one is the fibrous protein. So, they have very much regular structure, very well, like it will have plated sheet, it will have helices, and these fibrous proteins are insoluble in the water, and few examples of the fibrous proteins are the collagen, keratin and myosins. So, these fibrous proteins are mainly found in the muscles and the connective tissues. Next category is the globular protein, which contains different structural elements like alpha helix, beta sheet, unordered and beta turn, and these globular proteins are soluble in the water. And in globular protein, if you just say its 3D folding, so the apolar amino acids are mainly located in the interior, or you can say the core. In the core, it is having a hydrophobic core, whereas the polar residue are found in the periphery. It means shell, hydrophilic shell. And few example globular protein includes many enzymes, then immunoprotein like antibodies, even the extracellular matrix protein like albumin. So, basically if you see the fibrous protein, they are mostly in the connective tissues or muscles, but the globular proteins are majorly found, and they are the part of extracellular matrix, they are the part of plasma, you can say they are the part of the whole blood. So, whenever there is some sort of biointerfacial interaction take place, so only globular proteins are the involved, because when you are taking a biomaterial, it is coming into contact with body fluid. So, body fluid mainly consists of the globular protein. So, it is like an interaction between the globular protein and the surface. So, one more category is there, this is called the solvated or flexible proteins. So, you can say this is intermediate between the globular and fibrous proteins. So, it includes the disordered coiled like structure, and few example of this category is caseins in the milk and gluteins in the wheat grains. So, this is like a solvated as well as the flexible proteins, gluteins and caseins. So, these are the three category of the protein. Here we are classifying based on the 3D structure, fibrous, globular and solvated. So, mostly we will deal with the globular protein because they are the major component of body fluid. So, I have listed few functions of proteins. So, the first category, as I told, all the biochemical reactions are catalyzed by enzymes, and enzymes are the protein. So, whatever biochemical pathways are taking place inside the body, all are catalyzed by the enzymes. Other category is the transport protein. So, the proteins are responsible for transporting the oxygen, they are transporting the hormones, they are transporting some other substrate or other metabolites. So, these one function is the transport protein, and then next category is the messenger proteins. You can also say the signaling proteins like hormones, integrins. Next category is the immunoprotein like antibodies, which defends the body against any foreign attackers like virus or any infection. So, this is taken care by the immunoproteins or antibodies. And other category is the structural protein, which regulate the elasticity and structure of connective tissues as well as the mechanical strength like the of the muscles. So, these are the few categories, you can say that you can classify the functions in as enzymes for biocatalysis, transport protein for transport of various substance or compounds, messenger proteins for the signaling, immunoprotein for the defense, and structural protein for the elasticity or some sort of structure, mechanical work like muscles. So, these are the different functions of the proteins. Now, as we know, the proteins are made of amino acids, and amino acids are the polar non-polar, charged. In the charge it can have the positive charge as well as the negative charge. So, different non-covalent interactions are present. Non-covalent interaction means first is the covalent bond, that is the peptide. Apart from the peptide bond, or you can say the NSCO bond in the primary structure, there are other non-covalent interactions because of the different R groups of the amino acids. So, this is the hydrophobic interaction between the hydrophobic amino acids, electrostatic interaction between the charged amino acid, dipolar interaction between the, because there will be the formation of dipoles because it is having a amine group, carboxyl group, there will be dipole formation, and this van der Waals dispersion interactions as well as the hydrogen bonding. So, these are the few intermolecular interactions present in a protein. That is why if you remember the, when we discuss the various intermolecular forces, we discuss in a protein at the same time multiple intermolecular interactions are present. So, this is one example that you can say hydrophobic, electrostatic, dipolar, dispersion as well as the hydrogen bonding interactions are present in a protein molecule. So, hydrophobic, if you remember, we discussed the globular protein. So, globular protein is having a core, you can say this is a core and this is a cell. The core contains the apolar amino acid or the hydrophobic core, and shell contains the hydrophilic shell. So, as hydrophobic side groups are buried inside the core or the interior of the protein molecule. Now, if you want to see what is the contribution of the hydrophobic interaction, so that can be calculated or estimated by comparing the native unfolded structure and the native folded structure, because in case of folded structure this hydrophobic groups are buried. So, if you calculate the change in the free energy of the amino acids minus change in the free energy of the glycine, because if you in the glycine it is having no R group is simply hydrogen atoms. Standard difference in the standard molar Gibbs free energy during transfer of R group from non-polar to the water, from a non-polar medium to the water medium. So, the same delta G will be equal to the hydrophobic interaction. Why we are considering the glycine? Because glycine does not have any R group. So, it is having glycine C NH2 here R group is also H. So, hydrophobicity we are defining as change in the standard molar free Gibbs energy during transfer of a R group from a non-polar medium to the water. R group of the particular delta G standard Gibbs free energy of the amino acid minus delta G of the glycine. Now, delta G standard of a particular amino acid can be calculated simply based on the partitioning coefficient, means what is concentration of that particular amino acid in the water as well as what is concentration in the non-polar. So, delta G of that particular amino acid will be RT ln K. This is a at the equilibrium, what is its fraction or concentration in the water and what is its fraction or concentration in the non-polar medium. So, based on this we can calculate the value of standard Gibbs free energy of a particular amino acid, and then from there we can calculate delta Gr, and typical value of this delta Gr is 9 to 11 kilojoule per mole. Now, if you are calculating the delta Gr, if its value is positive, it means if its value is positive means there is a more affinity towards the water. There is a positive means there is a more affinity towards the water. If it is delta, if its value is positive means non-polar should be higher, than polar is higher means again this value will be in the decimal point, and again log value will be negative. So, total this will be the positive value. So, this will be greater than 0, it means R group is the hydrophobic. Now, again if you want to say this, if its value is negative means the concentration in the polar is the higher, it means this ln value will be greater than 1, then this whole function or whole value will come out to be negative. It means if delta Gr is negative means R group is hydrophilic, it means more affinity in the water phase. If its value is greater than 0 means it is having more affinity towards the non-polar phase. And the typical value of, you can say, the hydrophobic interaction or Gibbs free energy of transfer from non-aqueous to aqueous medium of a R group is 9 to 11 kilojoule per mole. So, electrostatic interaction, as we know, there may be the positive charge as well as the negatively charged amino acid. So, in between these charged amino acids there will be the electrostatic interaction that is given by the Coulomb's interactions. So, Coulomb's Qi charge of I, Qj charge of j, 4 pi epsilon r epsilon naught into r square, distance between the Qi and Qj, and epsilon r is the, this depends on the particular type of the environment, what is the ambience, and value of epsilon for water is 78 or 80, and for the interior of the protein its value is of epsilon is 5. So, we can calculate the value of electrostatic interaction using Coulomb's equation, and if you see any folded native protein, the charge is located at the exterior of the protein molecule. So, if the charge residue are the present at the exterior, so between the protein interaction also there will be the role of electrostatic interaction, as well as if you are having some charged surface and protein is also having charged amino acid on the surface, again there will be the electrostatic interactions, and that interaction we can calculate using simply the Coulomb's equation. The next interaction which is present is the dipolar interaction. So, as this is a glycine, as I told, it is having amine group and carboxylic group. So, there may be the formation of the positive charge NH3 and negative charge COOH. So, there will be now dipolar interaction. So, dipolar interaction we calculate first dipole moment. Dipole moment is the Q, the charge, L is the distance between the two charge, plus Q and minus Q, and this is listed that for dipole moment for water is 1.84 dBi, and for that one amide group is 3.7 dBi, and dBi we define when they are equally charged plus Q or minus Q 2 units are located at a distance of 0.02 nanometer. At that time the value of mu is known as 1 dB and its value is 3.336 into 10 to the power minus 30. Now, there can be two different kind of dipolar interactions. One dipolar interaction may be the interaction between protein and the solvent, let us say water molecule. Other dipolar interaction between the group of proteins. So, dipolar interaction can be within a protein or it can be protein between the proteins or it can also be between the protein and the environment or you can say the water molecules. So, depending on the given situation there can be different kind of dipolar interactions with proteins. So, next is the dispersion force. So, as we know if molecules are far away they will attract each other by the London attraction or you can say van der Waals attraction force, but when they come closer, so because of the electron cloud they repel each other and that is known as the Born repulsion. So, combining those attractive and repulsive nature you can say the interaction is defined by the Lennard-Jones potential which is having both one is attractive term other is the repulsive term in the same potential. So, if you see here if it is far away R is high here it is going to have the attractive here is this is attractive potential, but once it comes closer sharply there is a very high repulsive. It is going to have both attractive as well as the repulsive. So, this is the dispersion. So, it comes between the all kind of atoms, it need not be the charge atom, it need not be the hydrophobic atoms. So, this London dispersion and Born repulsion works between the all kind of atoms. Now, next is the hydrogen bonding. The hydrogen bond formation takes place between the hydrogen atoms and the electronegatively like oxygen, nitrogen. So, here we just see it forms between the amide group and the carbonyl group. So, it forms between the NH and the CO of two different amino acids. Now, the distance between the H atom and OH atom is about 0.19 or you can say 0.15 nanometer, while if you just consider their radii which is responsible for the van der Waals interaction is the 0.27. So, the hydrogen bond it having the extra dipole as well as the extra dispersion because they are going to overlap within the van der Waals radii. It is 0.27 and it is 0.15 nanometer. So, it involves the extra dipole and the extra dispersion interactions. And delta G of hydrogen bonds between the amide and carbonyl group is its value is about minus 12 kilojoule per mole, while the magnitude of hydrogen bond in the water molecule and the peptide is minus 16.7 kilojoule per mole. So, there will be the intramolecular hydrogen bonding as well as the hydrogen bonding between the water molecules and the peptide chain as well. In the similar manner, if surface is having a particular functional group, so there may be the hydrogen bond formation with the protein and the surface as well. Now, few examples of hydrogen bond is in the alpha helix. In the one cycle we have 3.6 amino acids. So, there is a hydrogen bond between the carbonyl oxygen atoms of ith peptide means let us say 1 and amide group of the I plus 4. So, at the end of one cycle there will be the one amide group and one carbonyl group, and there will be the formation of the hydrogen bonds between the NH group and the CO group. Similarly, in the beta sheet, beta sheet may be the parallel beta sheet or anti-parallel beta sheet. In between the two beta sheets also there is a formation of hydrogen bonds. So, these are the different intermolecular interactions which are present in a protein because of different kind of amino acids, polar, non-polar, positive charge and negative charge. Now, when protein folds into a 3D structure, from the primary sequence to the 3D structure, so depending on the number of amino acid, it can have the n number of configuration, or there can be the n number of folding pathways of a protein. But let us say this is the local minima of the Gibbs free energy. So, whenever it reaches to the minimum value of the Gibbs free energy, that is the only stable state. So, whatever is the net result of interactions between the segment within the protein molecules and also segment and the environment or the solvent. So, this intraparticle as well as the interparticle interactions, this is the net result of that, and whenever there can be many minima. So, minimum means delta G value should be minimum or negative, and that point will be the, you can say, the equilibrium or the stable, or in other word you can say this is a native structure of the protein. So, as you know, this protein is made of different amino acids. So, if it is the primary structure, it is having more randomness than the compact globular structure. So, there should be decrease in the entropy also when it is going from random coil to the compact folded structure. And if you want to calculate the entropy of different conformation, it is simply Kb Boltzmann constant into ln sigma. The sigma is the number of different conformation that is possible, which depends on the how many number of amino acids are there, and that particular amino acid how many conformation it can adopt. So, we can calculate the delta S, delta H, then we can estimate the value of delta G, and when it achieves minimum value of, or you can say the local minima of the Gibbs energy, that is called the structure or the native folded structure of the protein. Now, if you put the protein in a aqueous environment, so it is possible that native may again go to the unfolded structure. Protein is coming from the primary sequence to the native globular structure. Now, again if you put in the aqueous environment, so depending on the interaction between the protein and the aqueous solvent, again it may go to the unfolded structure. So, if you want to calculate delta G, change in the free energy from the native to the unfolded structure. So, you can write what is the change in the enthalpy from the native to unfolded, and what is the change in the entropy from the native to unfolded. So, if you are getting this negative value of delta G native to unfolded, it means the unfolded state is, if you are getting delta G value negative here, it means unfolding is favored. It means native state is less stable than unfolded state. But if you are calculating this, you are getting this value of delta G positive, it means this reaction is unfavorable, means your native state is more stable than the unfolded state. and typical values of delta G vary between 20 to 60 kilojoule per mole for different proteins. So, now what it says is, if you put a protein in the aqueous solvent, so already protein is having different intermolecular structure, covalent interactions, conformational entropy, intermolecular interaction. Now, there is going to be more interaction with the solvent. It may be the hydrogen bonding, it may be the dipolar interaction, even it may be the ionic interactions. That interactions will have some change in the entropy as well as change in enthalpy, and subsequently there will be change in Gibbs field energy. And depending on the, if it is negative, means the native state is converted to the denatured state, or you can say the native state is less stable in that particular condition. Now, what are the different factors which are going to affect the stability of a protein? So, as we know, there are environmental factor. So, that may be the pH, it may be the ionic strength, it may be the temperature, it may be the presence of other substance, or even the surface. Surface we are referring here as the adsorption. So, even in the presence of surface also it may affect the stability of a protein. So, pH, as we know that a particular protein is having isoelectric point, it means at this pH value it is having no charge, or net charge is 0. Now, if you increase or decrease the pH value, it is going to have the either positive or the negative charge, and that charge is going to contribute to the intramolecular interactions, and that may lead to the unfolding of a particular protein. Also, if you are having some denaturant or you are having some other substance like you are having urea, then it decreases the solubility of a polar component in the water, and when it is decreasing the solubility of that particular proteins, so it means protein has to adapt to different conformation, and it may go from the native to the unfolded structure. In presence of surface, this is the body fluid, it is having proteins, and this is a surface. So, typically what happen in case of body fluid, the first water molecule will reach to the surface, followed by the proteins, then cells, depending on their diffusivity. The water molecule will have the highest diffusivity, followed by the protein, then cells. Then first water molecule will reach, then protein will reach, then cell surface interactions will take place. And depending on the interaction between the surface and protein, a protein may retain its native structure, which is necessary for the its function. Otherwise, depending on the interactions, it may also unfold or denature, and if it is unfold or denature, then its function is totally lost, and that leads to the biofouling, that is undesirable. So, whatever is the surface chemistry, or you can say the surface properties, so it may cause some, if it is having some charge group, it may also induce electrostatic interaction. It is having some hydrogen bond forming group OH, H or N group, it may contribute to the hydrogen bond. Hydrogen bond, if it is a hydrophobic surface, it may include hydrophobic interaction. So, depending on the surface properties, there can be different intermolecular interaction between the protein and surface, and the net effect of those interactions may retain protein in its native structure, or it may lead to the unfolding denaturation of that protein. So, depending on the what kind of intermolecular interactions are present, we can call the adsorption as a physical adsorption or the chemical adsorption. If only van der Waals interactions are present, or you can say this long range weak intermolecular interactions are present, then we call it as a physical adsorption, and it's in this case the value of change in enthalpy is about 20 kilojoule per mole. But if you are having the short range and strong intermolecular interactions like covalent, ionic, hydrogen bonds, then this type of adsorption is called chemical adsorption or chemisorption, and here that value of delta H is much higher as compared to physical adsorption. You can say almost 10 times higher than that of the physical adsorption. Now, next is temperature. If you increase the temperature, so both enthalpy as entropy is a function of Cp, or you can say the heat capacity. See, increase the temperature, there is increase in the heat capacity. So, both enthalpy and entropy is going to change. So, if you are increasing the temperature, means there is going to happen the enthalpy entropy compensation, and because of this enthalpy entropy compensation, the value of delta G is going to change, or you can say Gibbs free energy is going to change. And if this delta G native to unfolded is negative, it means it will lead to the unfolding or denaturation of the protein. So, if you see, that is why the protein structure is stable at very narrow range of temperature, that is very close to that ambient temperature. If it goes to the below the temperature, very low temperature or very high temperature, both may lead to the unfolding of the protein. So, if you want to see what is the Gibbs free energy of the native and unfolded protein, or you can say folded and unfolded protein, then experimentally we can measure what is the fraction or the concentration of the native and what is the concentration of the unfolded. So, you can consider it is going to the native is going to the unfolded state. So, at the equilibrium we can calculate the value of equilibrium constant K, and if you calculate the K will be the d upon n, and if experimentally we can calculate the value of K, then we can estimate the delta G as minus RT ln K. So, in this way from the experimental data, if you know what is the fraction of native as well as the unfolded fractions at the equilibrium, then we can calculate what is the value of delta G. Now, we will just see one quick example. A polypeptide chain alpha helix is completely fixed, where in unfolded state each peptide unit of polypeptide can attain 4 different conformations. Now, first we have to calculate change in the entropy from the transition from the alpha helix to the unfolded state, and it is given the polypeptide is having a protein is having 100 of amino acids. So, it says in case of alpha helix it is completely fixed, whereas in case of unfolded state the polypeptide can attain 4 different conformations. So, we have to calculate the delta H, and also at a given temperature of 50 degree centigrade we need to calculate the value of delta H. So, first we will see how to calculate delta S. So, if you remember, entropy is a function of Boltzmann constant into ln sigma. Sigma is the number of possible conformations. So, delta S will be the R times ln sigma of the unfolded minus sigma of the alpha helix. So, this will be R ln sigma of unfolded upon sigma of helix. So, in this value is in case of alpha helix it is a completely fixed, while in case of unfolded we are it is reported the 4 different conformation are possible. So, this will be the R times 4 to the power how many amino acid 100, 4 to the power 100, this much different conformations are possible, because each peptide unit is having the 4 different conformation and we are having the 100 amino acids, the 4 to the power 100. So, this will be the value of ln 4 to the power 100, this is the ln 4 to the power 100 into R. So, this value will come out to be 1152 joule per Kelvin per mole. Now, once this value delta S is known, now temperature is given 50 degree centigrade, it means 323 Kelvin. So, at this temperature we can just see what is the Gibbs free energy, and at the equilibrium delta G value should be 0. So, delta H will be T times of that delta S. The delta S is known to us, we will just multiply with the value of temperature and we will get the value of delta H. So, delta H is coming out to be 327 kilojoule per mole. So, here I conclude. So, I started with what is the protein, its basic of protein, what is the different structure of the protein, then alpha helix, beta sheet, these are the part of secondary structure, then primary structure, tertiary and quaternary structure, then classification of the protein based on the 3D structure, fibrous protein, globular protein, and intermediate between the fibrous and globular protein. Then we quickly saw the what are different function of a protein. Then if a protein is folding, then what is its free energy, or you can say the local minimum of the Gibbs free energy during the folding. What are different factors like pH, temperature, ionic strength, or even adsorption, how they affect the stability of protein due to the making and breaking of different intermolecular interactions. And then we also saw the one example that how we can calculate delta S and delta H, and ultimately also we can calculate the delta G. So, thank you.